and we will also have time for some questions at the end. So you can write the questions in the chat, and then we will raise those questions at the end of the presentation. So then I give the word to you, Divas.
Yep. Let me share. Yes. Welcome to you all in this presentation regarding sediment handling in the reservoir of hydropower plants. Uh, as of me, my name is Diwash Maskey. I come from Nepal. Uh, I'm a PhD candidate here. My main supervisor is Professor Niels Ruther, and co-supervisors are Professor Oddbjørn Bruland and Adjunct Associate Professor Siri Stockset. I started my PhD in 2019 and will be completing this year. Uh, the contents of my presentation, I will be giving you some backgrounds on the sediment yield and sedimentation rate and sediment this status in the project. Then something on sediment management strategies. We'll show you something on physical model study of a Binga power plant. Then numerical simulations of fine sediments. Then laboratory investigation for diversion inlets, and conclusion of all of those works, and some of the current works that's being undertaken. Starting the background on the global sediment yield, I'm presenting this chart to you, which was presented by Walling and Webb back in 1983. There are some updates in these maps, but the general trend is almost similar. So this map shows us the total suspended sediment reaching the ocean. And if we see this map, we see these black areas, which are the highest sediment yield areas, which produces more than 1,000 ton per kilometer square per year. And most of these areas are in Asia, southern part of the Europe, Mediterranean, and western coast of the Americas. Even though this is 1,000 ton per kilometer square, what there is a debate is that not all the sediments reach the ocean. So there may be some factors affecting here in these maps also. Then talking about the sedimentation rate in the existing reservoirs over the year, Basson in 2009 presented this map in IHR conference, where we can see that in every part of the world, the sedimentation rate is above 0.5%. The maximum being in the Middle East region at about 1%. So we can say it's 0.7 to 1% is the sedimentation rate in every part of the world. Similarly, another chart he presented during that conference is the year when 80% of the existing hydropower reservoirs will be lost. And if we look into that chart, then we see that in Europe and South America, it's 2080 when these reservoirs will be filled up. Whereas in Africa, it's 2100. And this 2100 is mostly because of the Aswan Dam, which is one of the largest dams in Egypt. But the year which is of a concern is 2035 in Asia. And this year is just 10 years away from now. And hence, this is not the future, but this, we can say, it's the present condition. It's a very critical situation here. Then I took this data from this globaldamwatch.org. This shows the planned dams and the dams under construction in different parts of the world. The yellow dots are the planned dams, and red dots are the dams under construction. And if we see, this is mostly in the Southern Europe, Asia, and South America. And if we overlay that locations on this sediment yield map, then we see all these planned projects, planned dams are in the area of high sediment yield. So in the future also, there's sediments, the dams will be affected by higher sediment productions. So it's not only the existing reservoirs which are being affected now, but the future reservoirs or the future dams, future projects will also be affected, and hence these sediment management strategies are very important to be planned ahead and to research more on this work. So in existing reservoirs, we need sediment management strategies to slow down the sedimentation rate and to regain the lost storage. And in the future reservoirs, we need these sediment management strategies so that we can plan ahead in time and in space for its effectiveness. There are 4 sediment management strategies as presented by Morris and Fan. So the first one is reducing the sediment yield from the upstream. This is done mostly in the catchment areas and in the rivers or streams above the reservoirs by vegetating the catchment area or by construction of the check dams so that to slow down the speed of the sediments reaching the reservoir. The second is routing sediments. This means we take the sediments away from the reservoir. Third is removing the sediment deposits. That is, once the sediments are deposited in the reservoir, we remove that hydraulically or by mechanized systems. Then the final one provided is the adaptive strategies. This is once the reservoir is completely filled, this strategies basically does not include sediment management, but what we can do after the reservoir is filled, like removing the dams or increasing the height of the dams, changing the operation system of the reservoirs, such things. My work in PhD is mostly related to routing sediments. In routing sediments, there are 2 ways how we can route the sediments. One is bypassing the sediments. That is, we don't let the sediments come into the reservoir. We make another conveyance system to pass the sediments away from the reservoir. Then another is sediment pass-through system, where we pass the sediment through the reservoir, through the dam, and downstream of it. So there will be some outlets in the dam structure or nearby the dam structures, so that whatever the sediments that are coming in is passed through those outlets. But I'm more focused with sediment bypass. And sediment bypass, it's nowadays the sediment bypass tunnels are mostly in practice. Many of these are built in Japan and Switzerland, where they have been successfully operating these things. New sediment bypass tunnels are being constructed in Taiwan. And even in sediment bypass tunnel, the efficiency and the volume of sediments removed or the particle size removed depends upon the inlet location. If it's the inlet is located at the head of the reservoir, or if the reservoir or the inlet is located within the reservoir. And my work is mostly related to the inlet location of the sediment bypass tunnel and the efficiencies or the effectiveness of the inlet location. So with all these background, so now I come to the tools that we use for sediment transport. In planning and designing, we start with works with the guidelines. We work with the codes of practice. We plan something, but in planning hydraulic structures to optimize it, then we use traditionally we have been using this scaled physical modeling works. This is one of the pictures from Nepal. The main advantage of using a physical modeling is the very quick and easy visualization of the flow and sediment transport in the model. However, physical models are very resource demanding in respect to space, time, and cost. Also, there are scale effects as we cannot scale down all the properties of the fluid and sediments. In the recent years, numerical modelings are gaining popularities, mainly because this is getting cheaper. Now, as we know, we can get now 8 cores of processors in our laptops nowadays. So this is gaining popularities. However, numerical models also have some disadvantages because these are all mathematical formulations, and different models are using different assumptions for solving these equations. There are averagings of values, so there are some problems with that, but these are getting better and more accurate by the day. However, in relation to sediment transport, also many of the sediment transport relations are empirical relations, and those empirical relations are put up in the numerical simulations, which also gives some errors. And one other disadvantage is for non-technical persons who it's very difficult for them to understand the results. And now, but hybrid modeling is the other step coming up, where we use both of these, use the advantage of both of these models to get a complete, to estimate or to get more complete picture of the problems. So in case regarding to the physical handling model, I'm presenting you the case of a Binga power plant. First, some introduction on the Binga power plant. So this is the main reservoir of the Binga. There is a rock-filled dam of about 107 meters height. This is the spillway. There is a SPP intake, which feeds for the turbines that generate 140 megawatts. This is the river feeding the reservoir, and there is another reservoir which also affects this reservoir upstream of this one. The project is located in Philippines. The initial reservoir volume was about 95 million meter cube. The reservoir volume as of 2015 is 21. That means only about 22% is remaining, and the annual sediment inflow is about 1.4 million cubic meters. If you put this reservoir in this chart of capacity inflow ratio and capacity to sediment inflow ratio, we see that in the beginning of the reservoir, this reservoir is located here. But now the reservoir is within this region. And this is a chart presented in the paper with Kondorf, where it says that these are the reservoirs where flushing is much more efficient. However, the major threat that this reservoir is facing is the sediment delta is approaching the intake, which is seen from more and more sediments passing through the turbines. And as the sediment delta is approaching to the intake, it's also going above. More and more sediments are going over the spillway. And when more sediments flow over the spillway, there is abrasion, which then weakens the concrete, and then there is this threat of the stability or structural integrity of the spillway and the dam as a whole. So to study or to research on the alternatives of sediment management studies, this is the region that was modeled in the lab here at NTNU. This is the model prepared of about 600 square meters in the lab. The inflow coming through here, spillway, intake, and this is a proposed location of a sediment bypass tunnel inlet. The model was prepared in 66.667. The finest sand that we could model here is with D50 of 0.3 millimeters, and even that 0.3 millimeters would be about 20 millimeters in the prototype scale. And during all the modeling works, about 35 tons of sand was fed in this model to see the sedimentation and these alternatives works. Since the bed the sand was very coarse. We only modeled with very high flow of about 4,000 meter cube per second with intake discharge of 100. The simulation time was about 125 hours in the model, which is about 42 days in the prototype scale. And the constant sand feeding rate was about 3 kg per minute. And after the initial current situation tests, we then constructed the sediment bypass tunnel inlet location, and then we checked the performance of this SPT in two modes, in sluicing mode and in the flushing mode, with the same inflow parameters as before. And to after checking the performance of the SPT, we then tried with some modifications at the SPT inlet to increase the performance of this this inlet. So we have one extended inlet so that the mouth of this inlet is much more in the reservoir, so that more sediments could be sucked in from the inlet. Then this construction of a guide wall in the reservoir, so that the flow is turned around and more sediments and flow is concentrated near to the SPTs. So all of these were done in the numerical models, in the physical model down there. So the results of the physical model study, what we observed is that in the current situation, in the current scenarios, the sediment built up will be building up slowly towards the intake and the spillway, but as the sediment buildup grows, then this channel is formed in the middle of these deposits, and then it is concentrated towards the spillway. So the reservoir will ultimately be transforming into a river, which transports all the sediments down to the spillway. Only very finer sediments were transported down the spillway, not the coarser particles that we fed. Then, as this bed moved near the spillway and the SPP intake, the particle size were increasing from the spillway. And the sediment bypass tunnel was in the sluicing was not very satisfactory, but the flushing from the SPT was found good. But we don't know anything from fine suspended sediments, which has a more volume in prototype than the coarser sediments, and also which is present in the reservoir at the current time. So we don't know anything. We could not get any concrete conclusions from the physical model about the fine sediments. So to know the transport and distribution of the fine sediments, I then use the numerical model SIM1 with a structured curvilinear grid, inflow and 3 outflow locations from SPT, spillway, and intake. The inflow, the model first, the numerical model was verified in the physical model scale with the inflow velocities and with the flow pattern, how the flow is moving in the reservoir, and also with the surface velocities that we have the measurements here. Once the model numerical model was verified in the physical model scale, it was scaled up to the prototype scale, and then 2 of the tests were done. One was in the high flood situation, and another is the annual flow situation. So the first, the 20-year period flood, which lasts for about 27 hours, increasing the discharge from 1,100 cubic meters to 4,000 meter cube per second. SPT flow is 300 meter cube per second, and total sediment inflow of about 0.6 million cubic meters. So 6 different cases we studied. In this one, mostly with the full supply elevations during the flood, with 2 different locations of the SPT and also with guide walls. So what we see here is this is a case C with SPT in this location. we find that there are depositions with the fine sediments here, the erosions on the outer banks of the bends coming in here, depositions over here. But we also find this deposition in this region, that which is much more closer to the SPP intake. And this is something that we did not see in the physical model. With the performance of the SPT, or in the current situation during the flood, what we find is that the sediment retention in the reservoir is only about 30%. So almost 70% of the fine sediments are passing down the spillway. And in case of the sediment bypass tunnel, we find that it's only about 10% is passing from the SPT. So SPT performance with the flood conditions is not that high. Then the another is the annual flow situations. I took the data from the annual flow from the reports that has values of above 450 meter cube per second. Then in 1 year, the value, the flow reached 1210. In that year, the water elevation in the reservoirs, the peak elevation was 572.6, and the total sediment inflow at those is estimated to be about, again, 0.6 million cubic meters. In this situation, 4 cases were tested. So case A is the current situation, where we again see the even in the annual flow, there are depositions of the fine sediments moving towards the SPP intake. But in case B, as we put a SPT here, then this progress of the fine sediments is decelerated, so it's slowed down. Regarding the sediment removal, the retention is about 60% within the reservoir, but we have now considerably increased the sediment passing through the SPT. So from 10%, it's at the current situation, it's 20%, just over 20%. But if we put the SPT at this location further upstream in the reservoir, then we can almost remove 30% from here. Another result with case D is that if the SPT is located further upstream, then we are able to remove more coarser particles, including these fine sediments here. So more coarser particles can be removed if we move the SPT further upstream in the reservoir. So concluding from these physical and numerical models, we can get the flow paths from the physical model. It's mainly concentrated to the spillway. If this is very high flow, the efficiency of the SPT is not very good during the high flows. But from the numerical model, what we find is that SPT decelerates the progress of delta towards the SPP. And if we add the two results, like if we say 20% of the during the annual flood, if we say 20% of the flow is removed from the SPT and 10% is removed during the flushing, which we did in physical model, then we see that about 30% of the sediments can be removed from SPT, and that's only in the operation days of about 12 days. Now these things we can use it for optimizations or in planning purposes. So other two conclusions are that if we shift the inlet upstream, we increase the sediment volume outlet, and we also increase the coarser particles removed. And sediment diversion is again related to the diversion discharge. From this result, what we conclude that we need to shift the SPT inlet further upstream. So in my next test, I modify this model into a river channel of width in the model. So this channel has the length of about 22 meters and the width of about 1.1 meters with the SPT at a bend, and it's at the outer bend and downstream of the center of the bend. The main objective here was to find or to reduce the bed load or coarser sediments going into reservoir, and to determine the relation between the sediment diversion with discharge diverted. So 3 discharges were tested, about 25, 35, and 50, with a diversion percentage of 15, 30, and 45% through the SPT. and the results that we get is that the ratio of sediments diverted versus the ratio of discharge diverted, it has a non-linear relationship. So we find that until 30% of the diverted discharge, there is a very steep increase in the sediment diversion, but then this sediment diversion rate decreases with the increase in the diversion discharge. Next, so to improve the sediment diversion at lower diversion discharge, we did another test to have guide walls on the opposite bank like this. So this is a sediment bypass down inlet, and these are the guide walls on the opposite one, so that we can move more sediments towards the inlet. And then frontal sluice type intake. So this intake was extended by about 30 centimeters, and the opening was on the frontal face of this wall, so that this is more of a frontal sluice type intake. We only tested one discharge for these two options, and the diversion percentage was from 7.5% to 30%. And what we found is that the guide wall improves this sediment removal efficiency from the SPT. However, the frontal intake does not show a very good improvement. It does not show improvement in the sediment removal. But these are mostly on the preliminary sediment that we collected. The results are, I'm working on more detailed analysis of these things, which may change some of these things. In conclusions, on the SPT inlet in the river, that we get more diversion once this inlet is located in the river section where the regulations of the reservoir does not affect, because then in the river section, obviously the hydraulic gradient is steeper, which has more sediment transport, and thus more sediments can be removed from there. We have a non-linear relationship between the diverted sediment ratio and discharge ratio, and we also see that if diversion ratio is increased above 0.5, then there may not be increase in the diverted sediments, because what we saw earlier is that at 50%, almost 80% of the sediments incoming is diverted. And at last, the guide walls on the opposite bank improves the sediment diversion efficiency. So currently, there are some works being undertaken with the master students in their thesis. So HECRAS released this version 6 with the sediment transport capability in 2D. So we are testing this HECRAS for this long-term sedimentation study in reservoir, and optimization works in the diversion inlet in the river section. So one of the MSc student is working with the same Binga model to look into the long-term sediment transport and deposit sedimentation in the reservoir. And one of the student is trying to model this stream river channel to optimize, to see optimization ways to improve the sediment efficiency into the diversion inlet. So yes, that's from me. Thank you for listening to this.
Thank you, Diwash. Thank you for your presentation. I see there's a comment here from David that I can read up, but also if you have any questions, please write them in the chat and we can go through them one by one. The commentary from David is that it was interesting to see that the new projects for the hydropower reservoirs are coinciding with the areas with high sediment yield. And why do you think that is? Are the other projects already built out, or why do we see this now?
I guess because Asia is economically growing country, the south of the Europe or the Mediterranean economically growing, South America economically growing, so they need energy. And also, I guess more the water hydropower is not that exploited in those regions. So probably I think that's why there is more development there.
Yeah, I see Niels Ruter also comment on the same.
Yeah.
As per today, a lot of hydropower potential cannot be set in place because of sediments and the cost they cause.
Yeah.
So what's your next steps with this sediment bypass tunnel? Do you think you will get it constructed somewhere? Have they constructed some similar types of this before, or is this like a pioneer project?
No, the sediment bypass tunnels, yeah, they have constructed in Switzerland and Japan. They have constructed there for years. They have many of those and there. But now, since sediments are getting more attention because the reservoirs are getting filled up, so all the other the projects or the other areas or the countries are trying to find more on this sediment bypass tunnel, and there is always areas of improving the efficiency of that bypass tunnels. There are other problems also with the tunnels, but my focus currently is at the efficiency of removal. So yes, there is lot of things to work, and also in planning these sediments bypass tunnels, if we plan ahead, then yes, we have this one strategy placed already to tackle with the sediments. So this is where I'm looking into. So this.
Another question from Arne Koksæter. On the input of sediment load, you mentioned 20 millimeter prototype particle size. Is that a smaller size, or do you input a range of particle sizes? Just to,
If you would be,
I didn't follow that in there.
is the smallest size or is no? That is a D50 size. I think I've mentioned that. So that's the D50 size. How is that? Do you input a range of? Okay, so this 20 millimeter prototype, because in the physical model we cannot go below 0.1 millimeter, because then the cohesiveness starts with the particles. So we have to start at 0.1 millimeter, and that, so D50 being 0.3, that scales up to 20 millimeter in the prototype. So that was the, I think it has to do with the limitation of the particles that we can model here without getting cohesiveness cohesion in the picture.
Yep. Next one is from Siri Stockstedt. She has a comment. I guess we can also conclude that there are still complex issues to study to improve sediment management in reservoirs. And then SPT are very debated because they have a high investment cost. Yeah, that was also my my next question. So that will be a part then to look at this of the efficiency, and then looking at the costs together with other types of
Yes.
Yeah.
So yeah, so there are many issues, but so with the same, my focus is to improve the efficiency in one layout. So with the same infrastructure, if we can increase the efficiency of that system, then that is much more beneficial. So that is where I've been looking into these days.
Then we have a question from Stasha Öderud. Considering that the hydraulics will change due to the climate change, etc., how many years into the future are your sediment models valid for?
I am actually I am not modeling with the sediment yield or these things. So the model that I'm using is, it's not for sediment yield or sediment productions estimation, but I'm just modeling how the sediments will be transported and distributed in the reservoir. It's a very challenging field, I suppose, because yeah, it's sediments. It's always been very difficult to estimate. So yeah, it's a very large field. So yeah, I don't know how many years. I cannot say as a fact, but it's very challenging. Yes, a lot of the works are also being done to estimate on how much sediment is produced in a catchment, but yeah, they're all estimates. And these climate change, rainfall pattern changes, rainfall intensities, there are many parameters that affect these things. So it's difficult to say.
Yeah, I think that was the last.
Yeah.
Another one coming. We are trying to find relations for SPT for all kind of sediment loads, but the yield is supposed to increase in areas with large precipitation.
Yeah.
Seems like an interesting field, though, with more projects coming up in these areas, more sedimentation. So
Yes.
either way, it's an area worth exploring more and finding optimal solutions for, both in terms of efficiency and cost, of course.
Yes.
Yeah. Final comment there from Stasha. I appreciate the challenges you are up against. Happy you are working on it.
Yeah.
So
We'll be working on this for very long, I guess.
yeah, though it's not a quick fix to that problem, but
Yes.
yeah, we need to look at it from different areas and different angles. So I think that was it for now. No more questions coming in. Then I say thank you to you, Diwash. Thank you for your presentation.
Yes. Yeah. I'm happy to present these things, and thank you for this one, for the
And we
opportunity.
will also share this presentation on YouTube, and there you can also find all of our other GodForskerMorgen presentations as well, if you want to go and have a look at those. So thank you so much, Diwash.
Yeah. Thank you.
Okay, everyone. Bye-bye.
Bye bye.